gonna introduce about homojunction and heterojunction. As you can see in this, as you can guess in this name, homo means one and hetero means more than two. So, in the past of the history of the semiconductor, we usually used homojunction like a PN diode, but nowadays we usually use heterojunction. To boost the tunneling efficiency, the band-to-band distance must be very short or thinner for the lateral direction distance. And as you can see in this diagram, left side is the homojunction and right side is heterojunction. For the left side of the graph, it is kind of like a PN diode, PN junction. It has more bigger depletion region than the heterojunction. So the heterojunction has more carriers that tunnel through the barrier. For next page, I'm gonna talk about more about the heterojunction. For the heterojunction, it has more operation. It has more efficient operation concerning about the driving boosting, because band-to-band thickness was very thin to efficient tunneling. And if for the heterostructure, if there is a band of offset, we have to make the junction boundary more abruptly or more steeply, and this is depend on the heterostructure's device's design. The reason why the offset is so important is because by the offset, the tunneling probability is decided, and not only the tunneling probability, also the which bias we give could occurring the tunneling. So like threshold voltage, and to design the threshold voltage or of current, we use this offset concept in previous by simulation. And for next page, if you see the left side of the TFET, we use Induna Asan. It has more thick band-to-band, but at the left side of the indium asan and gallium, TFET has more thinner band distance. So the left side of the TFET has more tunneling current, and each driving operation will be more efficient than the left side of the picture. And this is the for homojunction below the heterojunction. Heterojunction is more higher driving current than homojunction. And for this page, we have talked about TFT demonstration challenges. To tell the result first, we use high K material for the TFET. But there is also disadvantages of the high K material. It is really hard to use because of the thermal budget and the defect issue. Also, if we use the high K, the leakage current trapping was the very highly important issue. And to overcome this, we do not full cover the gate drain by the gate because we don't want to control drain as well. We just leave it alone and we just cover the source and channel by the gate. So we solve the problem by this mechanism. And as you can see in this diagram, if the thickness of the oxide is getting smaller, the channel thickness will gonna getting smaller as well. And by this phenomena, if we give the gate bias between source and channel, the field will gonna be very effective to them. But if this mechanism is very hard to realize, then we use multi-gate structure for a better device. And for last, there is advantage and disadvantages of using threshold, not threshold, the tunneling FETs. The advantages of the TFET is it has steep subthreshold slope, lower than the 60 mV per decade. As you know, the 60 mV per decade is Boltzmann limit, and for second, large on current and off current is let you, and third is geometric scales is very good, and some designs are compatible with conventional silicon germanium and silicon CMOS process. But the disadvantage of the TFET is it has poor experiment derived current and bipolar conduction. And bipolar conduction is very hard to make CMOS because if it is in bipolar, MFET and PFET is both on, so it could not operate as a CMOS switch. And asymmetric device behavior, not good for the memory application. And last is the most attractive at very low operating voltage, but this is actually could be a disadvantage. But this is very bad for driving current because driving current is so low, and so we could not use a device like a motor or OLED panel that consume a lot of power. Thank you for listening.